Okay, I apologize. I just realized that I had the permissions wrong on the lecture slides for this week, so I've just corrected that, so they should be visible now. So what we're going to do is we're going to start by talking about recurrent neural networks, and then if we have time left over, we'll continue with the image processing that we were talking about last week. And you should also keep in mind the first assignment is due at the end of this week. Yeah, so if you, I think all of you have started on the assignment, but if you haven't made much progress, then you need to get moving. Okay, so what we're going to look at is different ways of processing temporal sequences. So what we've looked at so far is kind of static input. So you're given an image. It might be a very sophisticated or complicated image, but it's like one image that's presented at one point in time, and then the network has to process that image or that input and produce an output. But sometimes we want to actually process sequences of inputs. So language processing tasks, handwriting, stock market analysis, various things like this, speech processing. And so we're going to look at some different architectures for this, moving along from sort of very primitive approaches to slightly more sophisticated and, allowing for longer and longer range dependencies. And then next week we'll be looking at how all of these things can actually be applied in to actual systems for speech processing and text processing and so on. All right, so yeah, this is the kind of task that would involve temporal sequences, so speech recognition, time series prediction, machine translation, handwriting recognition, and so on. Now, the very first attempts to do this back in the 1980s, or at least the early attempts to use the first attempt to use a neural network to do this was the NetTalk system. And so the task here is simply to input some English text and pronounce that text. Now, English and French are languages in which this is a notoriously difficult task. So there are some languages like German and Italian where it's, or perhaps even Japanese, where if it's hiragana, where this task is quite easy because there's a huge, mostly regularity in the way things are written. But English and French, because they were written down early and the pronunciation changed over time, it's actually, there's a lot of irregularities and exceptions and so on to these, how things are pronounced. And so, this is actually a non-trivial task. So, the input is a sequence of letters. There were 29 possibilities for each letter. So I think it's the 26 letters of the alphabet, and then there's a space and a dash and a full stop or something like this. Three different punctuation marks. And the system that these guys, this was Sinofsky and Rosenberg in 1987, the system that they came up with was a sliding window approach. So they have a neural network. So the neural network itself is quite basically the same kind of architecture that we were talking about before, these old like two-layer neural networks with a hidden layer. And so it would... But the interesting thing is the way it dealt with this time sequence. So it was like a sliding window. So it would be given a sequence of only 7 letters or 7 characters with the inputs, and then the output would be like one of 26 different phonetic symbols. So these, the output was based on the International Phonetic Alphabet. And yeah, just to prove to you that this is not a completely trivial task, you kind of look at little subsequences and try to think about how how the vowel in the middle would be pronounced depending on what you see, right? So pa, pat, pate, paternal, those are actually 4 different letters in the phonetic alphabet. Mo, mod, mode, modern, right? So it keeps sort of switching around. Yeah? And you see quite a lot of this in English. The presence of an E lengthens, changes the quality of the previous vowel and so on. Double letters. So this is actually the network that they had. So they encoded each letter as a one-hot representation. So there were 7 groups of inputs, one for each letter in the sequence, and then for each letter they had 29 different inputs. Yeah, it's one hot. So if the letter is D, then the input corresponding to D would be equal to 1, and all the other 28 inputs would be equal to 0. And then they had 80 hidden units and 26 outputs. So this is based on the phonetic alphabet. So that symbol there is just K. Now, this system was sort of controversial in a way. It gained a lot of media attention. These guys were very good at getting themselves on the television. Even for me, this is something I heard about afterwards, but apparently they got themselves on some TV shows. And the thing was to publicize the thing, they hooked the output up to a speech synthesizer. And so what would happen is very early, when it hadn't had much training, it would produce this noise that sort of sounded a bit like a babbling baby. And then when it was fully trained, it actually pronounced the words mostly correctly. Of course, it was a very robotic sounding voice, not very different from the modern speech synthesis that you get from Mac, voice to text, text to voice, and so on. But people thought that was kind of cool. But serious people working in the field kind of pilloried them and criticized them because technically what they did was actually pretty poor. And it was quickly shown that a different type of machine learning algorithm called a decision tree could produce equally good or better accuracy and would be trained in a tiny fraction of the time that it took to train the neural network. Anyway, it would sort of spark people's interest in this kind of approach. And yeah, but it can only learn short-range dependencies, not medium or long-term dependencies, and that's fairly obvious because the output can only possibly depend on what's inside the window. If there were, which in this case is usually enough, but if there were a case where you needed to see a letter outside the window in order to correctly predict the pronunciation of something, then it would get that wrong because it's not seeing what's outside the window. Okay, so that's the sliding window approach. Now then we move on to what's called the simple recurrent network. So this was Jeff Ellman in 1990. So what happens here is it's a temporal sequence of inputs. So, there's a couple of different ways to describe it, but probably the most straightforward way is to say that there's a certain set of, the hidden units at each time step, the hidden units from the previous time step are copied to another set of units, which are called the context units. And then at the next time step, the input is presented, and the input comes from both the inputs and the context units are connected to the hidden units. So I don't know if it makes this perfectly clear, but I'm going to show a couple of different pictorial representations for this so that hopefully you'll get the idea. So you, at the first time step, I think I can point with this. Right, so these are the input units. So, let's say that we were going to do the net talk task. We could present one letter, encoded as a one hot thing, and then you would calculate the hidden units and the output units. And then what happens is those hidden units get copied to here, and then the next letter is presented, and you see that the hidden units at that time step depend not only on the second input, but it's whatever the value of those hidden units was at the previous time step. So this is called a recurrent neural network. Recurrent is a word that means running back into itself. And networks, the other type of neural network that don't have these connections are called feed-forward neural networks in order to make the distinction. Right? Now, this might be a slightly better way of looking at this. Some of these images I've taken from a blog post. I got the reference at the end of the lecture slides. I think it's I think this is Christian Herter's graphics. And so we could just, if we want to sort of draw it in a more compact form, we could just draw it like this. So this is the inputs, that's the hidden nodes, and that's the output, and then this arrow here is meant to indicate that the activations at the previous time step are feeding into the activations at the current time step. So this is just an abbreviated way of drawing this, and we understand that there's a time delay in this arrow here. Now, how would you train something like this? Well, if you sit down and think about it, it's kind of, you can kind of figure this out. But let's suppose that, basically you can, if you know in advance the length of the sequence, or you have an upper bound on the length of the sequence, then you can actually unroll that recurrent architecture into a feed-forward architecture. So let's say we know in advance that we're only going to have to process 10 inputs, then this would actually be equivalent to this architecture here. So you feed in the first input, you calculate these hidden nodes, and then you feed in the second input and you calculate these hidden nodes. And remember, what these arrows mean, that's not just copying from here to here. What this means is that there are weights that connect. There are multiple units here and multiple units here, so the arrow really means that every unit here is connected to every unit here with some weight, right? And then every unit here is connected to every unit here with some weight, and those sums are added up, and then the activation function is applied. So all the previous stuff that we've talked about neural networks is just kind of suppressed in this picture. So we calculate the hidden units of the second time step, and we make a prediction. And the third time step, now depending on the task, sometimes in some tasks we're doing an output at every time step. In other tasks we might be waiting until the end and just producing an output at the end. But this is the most general situation. Now, how would we train this? Well, we can do it by backpropagation, because now that it's unrolled, it becomes just simply a feed-forward architecture, and we can backpropagate this. So if let's say we have a target output everywhere at each time step. So we take this actual output minus the target output, and we look at the square of that, and we differentiate, and we differentiate that, and we backpropagate the differentials to here, and we backpropagate the differentials into these weights. but we also backpropagate the differentials into these weights, and we combine it with differentials that come from the difference here between the target and the output, and then these differentials get backpropagated into these weights and into these weights, and we can backpropagate through the whole network. Okay, it's unrolled like this, but we have weight sharing. The same way we talked about weight sharing with convolutional networks, we have weight sharing here as well, because these weights are actually, these weights are constrained to, sorry. These weights are constrained to be the same as these weights and the same as these weights and the same as these weights, and these weights are constrained to be the same as those weights, and these weights are the same as these weights. So actually, we calculate all these differentials, but then we aggregate them and update the weights according to those aggregated differentials. Okay, so this is an important concept. So is everyone happy with this? Does anyone have any questions about it? Yeah. And again, in the early days, or just a few years ago, you would have had to code this up yourself with the differentials and so on, but TensorFlow and other similar systems now will calculate the differentials for you by automatic differentiation. Yep?
So the arrows between each or A,
yeah.
is that the same output that goes to, let's say, H0?
The arrows, so each arrow is actually really a matrix multiplication, because it's taking all of those units and multiplying each one by a weight and adding them up. Yeah?
Is there a weight between, like, say, the first unit, H0 or 0, and the second one? Are there weights between the first block and the second block?
The first A and the second A. Yes, so that arrow from the first A to the second A, which is the same as this arrow here, what that really corresponds to is these weights here in this picture. So the first A is here, and then it's been copied down to here, and then those activations get multiplied by these weights. And these activations get multiplied by these agents, they get added together. Yeah. Does that make sense? So I think, yeah, this picture probably gives a little bit more detail what's actually going on. Yeah?
How do you perform the aggregation of the weights?
The aggregation of the weights. Well, as I say, like these days TensorFlow will do it for you, but what you do is you just have you keep the differentials in a matrix. Well, the weights are actually a matrix, right? So yeah, you keep the differentials in a two-dimensional array, and you just kind of you initialize that array with zeros, and then when you backpropagate here, you add the differentials, and then when you backpropagate here, you add those differentials to the same array, and you keep going, and then you multiply the whole thing by the learning rate, and then you add that array to your array of weights. Yeah. So it is kind of, in a way, it is kind of instructive. It's helpful in a way to implement these things by yourself in MATLAB or something, because it sort of helps you to learn what's going on. Yeah. But that I think you can imagine, because you've all taken a data structures and algorithms course, I think you can all sort of imagine how it would be done. Yeah. Yes.
So in the previous slide, which we have.
The context layer. Yeah. I realize now I should have put the context layer on the left-hand side. It would have matched up a bit better with the other picture. But yep. Their activations will also contribute to the next value. Their values will contribute to the next values of H1, H2, and H3. Yeah.
So they have
these dotted lines are not weights. So the dotted lines is simply copying. Yeah.
There are also the lines from S1 to H1, H2, H3. So they are also taking part in that computation as well.
Exactly. That's right.
They will have some weight when they will be taking part in that.
That's right. Yeah.
Is that different from I1?
Different from which?
I1, like the weights to I1.
Different weights. That's right. Yeah.
Is that every time we just copy H1 to S1?
That's right. Exactly.
Nothing else, just copy.
Just copy. Yeah. Good. So, okay. Now that's the sort of, so that's the most fundamental architecture. That's called the simple recurrent network, or sometimes called an Elman network. Now, sometimes it's helpful sometimes to, there are other versions of recurrent networks that are just slightly different. So sometimes it's helpful, if you look at the difference between this picture and the previous one, the only difference is we've added shortcut connections from the input to the output. So this was, when we went back and when we did the if we go back to the two spirals task, we found that shortcut connections sometimes were helpful. So sometimes we add those extra shortcut connections, but it doesn't, it doesn't change the recurrent part really. It just changes a little bit how the outputs are computed. And in the early days, there were also Michael Jordan, not the basketball player, but a different Michael Jordan, did some experiments where he had connections going from the output back to the hidden. And so occasionally people do that as well, and that's sometimes called a Jordan network, if you see the phrase Jordan network. So occasionally we have recurrent connections going from here to here, or shortcut connections from here to here. But the ones from here to here is the most common way of doing things. And later on we'll talk about LSTM, which is slightly different again. This is another kind of recurrent network that we played around with back in those days. This is sometimes called a second order network. Now, so the way this works is as follows. The input, this is designed for tasks where the input is either zero, you've got inputs that consist of sequences of zeros and ones, right? So for the net talk, we had 26 different levels of the alphabet, but sometimes when we look at formal languages, we just have zeros and ones, or if we had 26 letters, we could have 26. So here we have one set of weights for 0 and one set of weights for 1, and depending on what the next input is, this is the hidden unit here. So depending on what the next input is, we switch back and forth between these two sets of weights. Actually, if we had 26 letters, we could also have 26 sets of weights and switch between them. So again, this is another kind of network people were looking at. It's sometimes called a second order network because it's equivalent to saying that the weights get multiplied by 0 or 1. We've got some weights here that get multiplied by, these weights get multiplied by, if the input is 1, then these weights get multiplied by 0 and those get multiplied by 1. If the input is 0, these get multiplied by 1 and those get multiplied by 0. So you can write it as like a product. So that's why it's sometimes called a second order network. So all of these networks kind of do a similar job and can be sort of analyzed in a similar way. Okay, now I showed you before, remember when we did the encoder task, we were looking at how you could represent points in the hidden unit activation space as points in a two-dimensional space, and then we looked at outputs as lines in that space. Well, we can do the same kind of analysis here for these recurrent networks. So now what kind of tasks can we do? Again, this is sort of toy tasks, but it's, leading to the same methods. I'll show you later on how the same methods can be applied to really quite serious problems like machine translation and so on. So the task here is called formal language recognition. So you have a training set that consists of accept and reject strings, and you want to train your system so that it's given the symbols in the sequence one at a time, and then after it's seen all the symbols, it has to say whether that is an accept or a reject. So it's a classification. It's classifying the strings into two different classes, but it's just traditional to refer to them as accept and reject. This is from formal language theory. So in this case, what's the rule? If you looked at this and said, well, what's the rule for accepting or rejecting, what rule would you come up with? Yeah, if every symbol in the sequence is 1, then the string should be accepted, otherwise it should be rejected. And so if we train, well, okay, let's look at it two different ways. So we can build what's called a finite state machine to recognize one of these languages. Now, some of you may not have seen this. I don't know how much of this kind of formal language stuff you guys have seen before. Some of you may not have seen these finite state machines, but these are quite straightforward to understand what's going on. So you have a machine that consists of a finite number of states represented by these circles, and the initial state is represented by this arrow. And as you process these symbols, you transition from one state to another. So you start out in this state, and if you see a 1, you stay in this state, and if you see a 1, you stay in this state. But if you see a 0, you go to that state. And then from this state, whether you see a 0 or a 1, you go into that state. And then this double ring means that at the end, if you end up on a state with this double ring, then the string is accepted. And if it's just a single ring, then the string is rejected. So this is a very, very simple example of a finite state machine. In effect, this is heaven and that's hell kind of thing. Like once you've gone there, there's no coming back here. Now, interestingly, if we train a neural network, so in this case it's one of these second order networks, but you'd get a very similar result if you trained a simple recurrent network. And you can actually, this is actually a diagram that's generated from the network after it's been trained. And you can see there's 2 hidden nodes, and every dot represents a possible set of hidden unit activations as we process these strings. So you see, like that cross there is the initial state, and then as long as you keep processing ones, you actually kind of stay with these dots over here. But if you see a 0, then you go over here, right? So and then the dividing line ends up. All of these things are trained, of course, and the dividing line ends up being here. So the points that end up on this side of the line are accepted, and the ones that end up on this side of the line are rejected. Okay, so it's very similar, like I said, to what we look at with the encoder test, but there's some dynamics involved here as well. And so you can see that actually, and there's a procedure that will actually kind of extract this finite state machine from these dynamics. But I think you can kind of see that this machine actually captures the behavior of that network. Here's a slightly, all of these languages are relatively simple, but this one is slightly more complicated than the previous. So what rule, if you had to come up with a rule for what's accepted and rejected in this case, what rule would you come up with? Yep. Not right. So if it's, yeah, if there are 3 zeros in a row, then you reject the string, otherwise you accept it. Yeah. And that's a fairly, yeah, simple rule that is compatible with all this data, you know. Perhaps the simplest rule that's compatible with this data. We can argue about the definition of simple, but yeah, that sounds quite reasonable. And in fact, here's a machine that does exactly that. So again, let's look at the machine first. So you start in this state. You start in this state here. And then if you see a 1, well, if you see a 0, whenever you see a 1, you go back to this initial state. But if you see a 0, first you go to here, and then if you see another 0, you go to here, and if you see another 0, you go to here. So if you do if you see 3 zeros in a row, you'll end up in this state, and that's the only way you can get to that state. So that's this finite state machine, and on the left here is actually the dynamics of a network that's been trained on these input streams. So we train the network, and then what we see is that the activations fall into these kind of clusters. That's the initial state there, and when we apply, when the input is a 0, the dot moves from this cluster to this cluster, and from this to here and from here to here, and if it's a 1, these ones go back to this cluster here, whereas that one stays over there. So it turns out that this network, this trained network actually exactly, you know, the behavior is exactly the same as the this extracted machine. And you can further analyze the dynamics of this. It's sort of sometimes it learns something that actually isn't can't be captured by a finite state machine, but is actually sort of a bit chaotic in its behavior. And you sometimes get these phase transitions just from one training step to the next. So the weights have only changed very slightly from here to here, but if we plot out these dynamics for these weights, for the weights on the right, it's this regular behavior that's shown by the finite state machine. The ones on the left, it's actually this kind of more complicated structure. So all of these points are possible in the activation space. Okay, so that's so this is where you're sort of trying to learn languages that are defined by a finite state machine. Now, there's this, again, I don't want to go into all these details about formal language theory, but there's this thing called the Chomsky hierarchy, which classifies formal languages into different classes, so that the ones that can be processed by a finite state machine are called regular languages, and then you have context-free languages and context-sensitive languages and recursively enumerable languages. So there's a whole kind of bunch of theory behind this, but for our purposes, we just train networks on a few simple examples from these different classes of languages, and then try to analyze the dynamics. So a very simple example, well, a context-free language is something that can be processed with what's called a push-down automaton. So it's like a finite state machine, but it also has a stack of items, so it can put an item on the stack or take an item off the stack, right? But it's only got one stack, you know. And so an example of this is, of one of these context-free languages is ANBN. So ANBN means the string consists of a certain number of A's and then the same number of B's. You know, that n can be any number, but the numbers have to match. And then if you look at an example like ANBNCN, that turns out that's actually not context-free, but it belongs to this slightly larger class called context-sensitive. And if you, the highest, or the most general class is called recursively enumerable, and this is characterized by true quantitative Boolean functions, or you need a Turing machine to process these kind of languages. So we're just interested in like things like ANBN and ANBNCN. Now, the thing with the ANBN, if we try to think about this, there are structures in natural language that kind of mimic this. So some languages have center embedding of clauses, some have tail recursion. European languages tend to have center embedding. So you can say the evidence the lawyer presented was convincing. You know, this is an example of center embedding. You say the evidence was convincing, but then in the middle you say the lawyer, the evidence, what kind of evidence was it? The evidence that the lawyer presented. And then you can try to introduce more and more clauses in the middle. So you can say the evidence the lawyer, the gangster, retained, presented was convincing. And then you can say the evidence the lawyer, the gangster, the witness identified, retained, presented was convincing. So in sort of Chomsky's scheme of things, you could embed things as deeply as you want. You could have any number of embedded clauses and it's still a kind of correct sentence in English. But of course, if you try to embed more than about 5 or 6 levels, you get sentences that nobody can really understand because they just kind of lose track and get confused. And this sort of A and B and C, and it's hard to think of an example of this kind of thing in real language, but it's sort of like, I'm not sure, John, Paul and Ringo played guitar, bass and drums or something like that. All right, so let's look at this ANBN. So this is some work that was done by Wiles and Ellman in 1995. So the previous task was language recognition. You'd process the whole sequence and then you give one answer at the end. What they were looking at here is language prediction. So you're trying to predict the next sequence, your next letter in the sequence. And some of them are predictable and some of them are not. So in general, with languages, you often have a sort of probabilistic prediction. But in this case, I don't know when I start, like if you look at this AAAA, I don't know when the first B is going to occur. So I can't predict this AAA and that B. But once I've seen AAAAB, then I know that there are going to be 3 more Bs and then an A. You know, so half of those ones are predictable, but the other ones aren't. So when we do the back propagation, sometimes we only train on the ones that are predictable and not the others. Now, and this is the network that they use. So again, this is a simple recurrent. This is the third picture of a simple recurrent network. So we had the one where we explicitly had the context units. We had the one where we just had the little arrow. In this case, we show the hidden units being connected to themselves, but we understand that this is with a time delay. So for this task, we represent A as 1, 0 and B as 0, 1. And so we present the first letter and then we calculate the hidden and the output, and then at the next time step, we use the recurrent network connections as well. And the output is, it's trying to predict the next sequence, but we only train for the ones that can actually be predicted. Okay, now why is this interesting? Well, when they did this task, what they expected was, they expected to see something sort of like this. You know, they expected that it would come up with some sort of finite state machine, but interestingly, it came up with something else, and it was able to generalize to strings that had where n was larger than what had been trained on. So in some cases, you train it up to a to the n, b to the a to the 10, b to the 10, but it could correctly also predict a to the 11, b to the 11, and a to the 12, b to the 12, even though it wasn't trained on sequences that long. And they found this quite surprising, so they tried to do this analysis of the hidden unit dynamics, and this is actually what was going on here. So at the beginning of the sequence, the hidden units are in this position here, and as it processes, so let's say it's going to process A to the 8 and B to the 8, so as it's processing the A's, it kind of oscillates back and forth like this towards some fixed point. And then when it sees the first B, it jumps over to here, and then when it sees additional B's, it oscillates outwards from that point there, and then when if there are 1, 2, 3, 4, 5, 6, 7, if there are 8 A's here, when it gets to the 8th B, is just enough for it to cross this boundary. So this is where the B's are being predicted, and this is where the A's are being predicted. So you can see why it's able to generalize. It just kind of oscillates in a little bit further here, and then when it jumps over, it starts from a closer point here. So so we did some follow-up work on this. We tried training the networks by a method called evolution rather than backpropagation. I won't go into the details of the evolution now, but later in the course we may talk about it if we have time. But it turned out the evolution produces results that are a bit more stable, but interestingly, sometimes the evolution produces dynamics that are monotonic rather than oscillating. So this is an example of a monotonic network. As it's processing the A's, it doesn't oscillate, but it just moves in one direction towards a fixed point, and then afterwards the B's move in one direction. But these monotonic solutions couldn't process the oscillating solutions could process strings that were longer than these monotonic solutions because they sort of had more space to move around in. And you can analyze this by looking at fixed points of these maps and calculating the eigenvalues of these transformations, and they're reciprocal to each other. And here's another task this is a related task. So here, instead of having all the A's and then all of the B's, we have a mixture of A's and B's, but the network is trying, the task of the network here is to tell us whether the number of A's and B's match. So, and what emerged, the dynamics that emerge here is actually a kind of spiraling behavior. So there's some fixed point here, and the activations are spiraling around that fixed point. So let's say we process this, but this sequence has several A's and then some B's and then some A's and then some more B's. So every time we see an A, we're spiraling inwards, and when we see a B, we spiral outwards. So we go A, and then B, 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 and then AA, B, 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 and that's the point where the numbers match. So this is on the accept side, but then if we have one more B, it'll go back over onto the reject side. Okay. And finally, Stefan Charlotte and I did an experiment for this A and B and C, and we used three. We couldn't do it with 2 hidden units, but we did it with 3 hidden units. So this is like a 3-dimensional picture of the hidden unit dynamics. And again, it's kind of a general. It's the same principles as the A and B N, but it's a little bit more souped up. So as it processes the A's, it's oscillating towards a fixed point here, but then as it processes the B's, it's actually, there's an attract, in one direction there's an attracting fixed point, and in the other direction there's a repelling fixed point. So you get this oscillating inwards in one direction and outwards in the other, and that produces this nice kind of star shape. And the same thing for the C's. Okay, so it's quite interesting. And then you can have monotonic solutions for this as well. So here the A part is, the A and the B part are, the A part is oscillating, the B part is oscillating in one direction and monotonic in the other, and the C part is monotonic. Any questions about this? Yes?
What does the H3, H2 represent?
These are 3 hidden units.
Is it like the confidence that it's that class?
No. The H1, H2, and H3 are simply the values of the hidden units. So in terms of the outputs, okay, we're not showing the outputs here. So in 2 dimensions, we show the outputs by a straight line. So in this case, this line here separates one output from another. And here it's this dotted line, and here it's the dotted line. Now in the 3-dimensional case, theoretically we should draw a plane, but it's too hard to draw it in the picture. Yeah. It's a good question.
Is that
Yeah.
essentially the actual value hidden unit is coming up with?
The dots are the values that the hidden unit is coming up with exactly. That's right.
So, let's say the coordinates, each little x, y, z, let's say, is the output of a hidden unit.
That's right. Yeah. Yeah.
Maybe you can count the alphabets or try to predict the sequence. So if A, B, and C, they have equal number of letters. So if we count the A, then it is sufficient because the B and C will have equal numbers. So we can just count the A, B, and C.
In this task, they have to be in the right order. So you have to have the A's first, and then the B's, and then the C's. Oh, how would we? Essentially, it is kind of doing that, but in different dimensions. So it's using some dimensions in the hidden unit space to count the A's, and using different dimensions to count the B's. Yeah.
Previously, in this week, we discussed the automata like machine. So, I mean, how's that incorporated with the neural networks?
Sorry, what was the question? Yeah.
Previously, we controlled the automata, the state machine. So, how's that is incorporated with the neural networks?
Well, 2 things. So it's possible, sometimes sequences are generated using this finite state machine, but in this case, there's actually in some cases like this one, if you analyze the behavior of the network, you can prove that it's actually performing this, that it's actually equivalent to the finite state machine.
So, this is just to verify maybe? Or
Sorry?
this is just to verify the result of
It's a kind of analysis, yeah, verification. Once you've done this, you know that it's going to process all strings the same as the automaton, no matter how long they are. Yeah. Good. Okay. Now, so everything we've done so far was these simple recurrent networks and these second-order networks, and they are able to learn these sort of relatively simple tasks, but it's hard for them to learn. They can learn sort of what we might call medium-range dependencies, but they have some trouble learning long-range dependencies. So in fact, I mean, if I go back to these examples here, to be honest with you, one of the things that, in order for this to be successful, there had to be a mix of different lengths of strings. So you'll notice how some strings are quite short, some are long. That's actually important for the training of these recurrent networks. If you trained it only on long strings, if you trained this architecture on only long strings, then it may actually struggle to learn the task correctly. And the reason for that is because of long-range dependencies. So if you it's hard to see a good example here, but if you had a string with 3 zeros and then 20 ones, the classification depends on those 3 zeros that occurred at the very beginning. So it has to kind of remember for a long time something that happened early on. And the same thing here. Well, this is probably a good example. This is almost all ones, but it has to kind of pick up on the fact that this 1 0 is necessary. And so this, when I guess it was basically Hochreiter and Schmidhuber who were looking into this, and they realized that there are limitations to these simple recurrent networks. They can learn things from a few time steps ago, but it's very hard for them to remember things that happened, learn to remember things that happened a long time ago. And in language, sometimes we have to remember things for a while as well with reference. So one example is gender. Some languages have gender matching. So, I say that a woman went to the shops and bought some fish and then went to the park and drove home, and then he cooked dinner. Well, in languages with gender matching, you notice that there's the gender of that later pronoun has to match up with the earlier pronoun, even though there may be a lot of stuff in between. And in languages that don't match gender, it may be something else. Like, if you actually want to understand what a sentence means, an object may be referred to in one sentence and then referenced in the next sentence. And you have to pick up on what the reference really means. Yeah. Okay, so these guys tried to come up with an alternative to these similar recurrent networks that would be able to learn longer range dependencies, and they came up with this system called long short-term memory, which has since become really kind of a standard in the field. And later on, a somewhat similar but a little bit simplified architecture called the graded recurrent unit was introduced, and there's been a bit of a debate about these two architectures. For a while, some people were saying that these GRUs were just as good as the LSTMs, but in the latest, just this year, there's been sort of other people saying that no, LSTMs are better. So I'll describe I'll describe the LSTMs first and then the GRUs. And these two are very good resources that explain these things actually very nicely with pictures and so on. So here's an example. Again, like I say, these are toy examples, but the LSTMs are used for serious applications now. But this is a sort of toy example that they use to demonstrate this. But this is, again, a finite state machine. And we want to use this for a language prediction task. And this is the initial state, and that's the final state. And sometimes, so you can, if you look through this reference, you can see how they try to train a recurrent network on this task, and then they try to train an LSTM. I didn't draw a picture of the architecture, but basically it's the same as what we looked at before, but there's 7 inputs instead of 2 or 3, because I think there's 7 different letters here, right? So there's one input corresponding to B, one corresponding to T, one corresponding to S and X and so on. Now, this technically what's drawn here is called a non-deterministic finite state machine, because some circles have 2 arrows coming out of them instead of 1 arrow, right? So what's an example? From here, you can have either S or X, and the assumption we make here is that they're equally likely. So, so in terms of the outputs, if the string you saw was BT, then what you should predict is 0.5 for X, 0.5 for S, and 0 for everything else. Yeah, so the output is intended to match the probability of the next letter that occurs. Right? And here's another example. This can be this would be 50% S and 50% X. Okay, so let's say the network input B, P, T, V, P. It would then the next letter is either S or X with equal probability. Okay, so this is the task, right? Yes.
Over time, does the neural net eventually get towards somewhat what the state machine? Or are they in different concepts?
It's a good question. So I mean, there's actually that web page does provide code for training this, but the code is not in TensorFlow. It's actually in Theano, and Theano is kind of like not really supported anymore and stuff. But I've had a play. You could have a play with. I've tried to. Maybe we should try to translate it into TensorFlow. But what happens? You can test it, and it does produce. Most of the time, it does learn correctly and produce the correct output. So you can print the outputs and check that it's kind of matches. But you were asking about the analysis. Would it have behave like a finite state machine? I think it would, but I don't remember how many hidden nodes they had, but I think they had about 5 or 10. So then the analysis becomes a bit more computationally expensive because there's so many hidden nodes. But you could, I think it could still be done. You could prove that it's, check that it's a finite state machine, yeah. Okay, so that's the Reber grammar. So a simple recurrent network can learn this. Yeah, this is basically the same as AN, BN, or I mean, it's the same as those other, those earlier tasks, except we've got more letters. We need more inputs and a few more hidden nodes, but it can learn the task successfully. but this is the one that the simple recurrent network falls down on. So this is specifically designed to be an example where you need to remember long-range dependencies. This is called the embedded Reber grammar. So each of these two blocks is the same as the Reber grammar we just looked at before, but there's this extra complexity. After the first B, you see either T or P, and then you have to remember whether you have to remember the second letter that you saw, whether it was a B, T or a P, because once you're in here, after that you don't know, there's nothing to give you a hint as to whether you're in this block or that block. And then until you reach this point, and then you're asked to try to correctly predict T or P, and it always depends on what you saw at the beginning, right? So it's a synthetic task, but it's specifically designed to be a task where you have to learn things from a long time ago. Yeah. Okay, so if you train a simple recurrent network on this task, it basically fails. It ends up when you get to this point here, it'll just predict T or P with equal probability because it hasn't learned the dependence on this thing from before. But an LSTM successfully learns this. Okay, so let me just quickly say what an LSTM is. So this is another way of depicting a simple recurrent network. So these inputs are being fed in. This is at each time step, and these are the predicted outputs. And this is the hidden node, hidden activation, and then so the hidden activation from the previous time step gets combined with the input, concatenated, if you like, with the new input, multiplied by some matrix. This activation function is applied, so it's usually, so remember this tan H is this one that gives you an answer between -1 and 1, and then that goes on and becomes the next hidden unit. Okay, so this is a simple recurrent network. Now, this is an LSTM. Now, it looks a lot more, there's a lot more complexity here, but let me just try to briefly explain to you what this is. Okay, so it has 3 different gating mechanisms. So first of all, let me remind you about this sigma and this tan H. So tan H, the sigma is a sigmoid, and then there's tan H. Now these two functions have the same shape, except that the sigmoid always produces an answer between 0 and 1, and the tan H produces an answer between -1 and 1. So just to go back here, all of these previous examples we were using the tan H function. So these hidden units, you can see that the scale is between -1 and 1 in that case. Now here the sigmoid is being used. You can see it's between 0 and 1. So what we assume here is that these hidden unit activations are bounded between -1 and 1, but for these gating mechanisms, we actually need a positive value that's between 0 and 1, because we're going to multiply it by something. Okay, so what happens is the hidden unit from the previous time step, the values from the previous time step comes in. Now here, this is actually an output, So now we're distinguishing this, what's coming along here is the hidden unit activations, and then this here is the output. And so the previous, the hidden unit activation from the previous time step arrives here, and the output from the previous time step is arriving here. Now the output from the previous time step and the new input are concatenated, and there's a kind of multiplied by a matrix, and then a sigmoid activation function is applied. And so for each vector, so remember that this is let's say there's hidden units are of dimension n, then this process here gives you n numbers, and each number is between 0 and 1, and this is called this first sigma is called the forget gate. So it's each hidden unit gets multiplied by that number. So if that number is close to 0, that means that if the number was equal to 0, if the number is equal to 0, then that means you're forgetting the value of that hidden unit altogether. You're multiplying it by 0. If it's equal to 1, that means you're remembering it completely. You're not forgetting it at all. And if it's like in between 0 and 1, you're partially forgetting it, right? So this number here is how much of each component to forget. Then this one here is called the input gate. So this sigma, so these numbers here are going to be, the tan H is going to be applied here to give you a new set of values. But instead of just this new set of values replacing the old ones, we're going to take a linear combination here. So the output of this sigma is telling you how much of the new value to add in there. So if this sigma is equal to 1, that means add in all of the new value for that component. And again, if it's 0, don't add in anything. And if it's in the middle, you partially add it in. Right? So you get a kind of the previous activation, some of it gets forgotten, and then some of the new, either some or all of the new activation gets added in. And then this third one is the output gate. So even after you've done that, then this goes through a tan H function, and there's another sigma that tells you how much of that to retain for the output. Yes, there's these 3 different gating mechanisms, and all of this gets trained by backpropagation. So that's the pictorial representation. Now here's a slightly different, it's just depicted in a slightly different way here with the equations. Yes? No. They don't have the same input. So this is, we haven't, different weights. Well, I don't know which picture I should be looking at, but let's look at this picture for now. So there's here, in the previous picture, the weights were kind of suppressed, but here, these weights are different from, so it says UW, 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 but these are actually different. This UW is different from this UW and this UW and this UW. Yeah, that's confusing. All right, yeah. So you see on the right-hand side, there's a little subscript. You've got WF is for the forget gate. WI is for the input gate. and WO is for the output gate. So somehow I apologize that in this graphic, this should be WF, this should be WI, and that should be WO. So we've just, the subscripts are missing, but these are different. Yeah. So we have this previous H gets multiplied by some matrix U. This X gets multiplied by a matrix W. Those things get added, and then the sigmoid function is applied. And then this is multiplied component-wise. So remember, if there's 20 hidden nodes, you get 20 numbers between 0 and 1. And this vector of size 20 is coming in, so you're multiplying the first component by the first number and so on. Yeah, it's component-wise.
Is the output of each sigmoid function only one value?
The output of each sigmoid function is only one value, but you've actually got, if this vector is of size 20, then you've got 20.
Modifying them.
Yeah, exactly. But each one is independently, the sigmoid is applied independently to each one. Yeah.
So in that example, FT would be also size 20.
That's right. Okay, so at least this gives you the whole picture. This tells you all the equations, and the thing is trained by backpropagation. So again, this is the advantage of the TensorFlow and the automatic differentiation. You don't have to you don't have to compute all these derivatives yourself. You just have to specify these equations, and it'll compute the derivatives for you, and you can kind of imagine what goes on with this training. So in the, I'm not sure, but so in the beginning, let's assume that these weights let's think about this for a minute. So if you assume that these weights all start with very small values, then this sigmoid function will be approximately 1/2. So in the beginning, it's approximately forgetting 1/2 of everything, inputting 1/2 of everything here, and then outputting 1/2 of everything here. And then as the training proceeds, some of those numbers gradually come up from one higher and others decrease. So somehow that happens in such a way that, so in other words, it's kind of if there's 20 dimensions in that hidden unit, it's kind of choosing some of those units I'm going to use to remember things for a long time, and other units I'm going to choose as sort of short-term memory. You know, I'm not going to, other units I'm going to use for only just processing what I've immediately seen. So you get this segregation of, you get this segregation of some units being used for long-term storage and some for short-term storage. And you can analyze these LSTMs as well. So I always get some people complaining, oh, why are you showing us this stuff? This is just toy problems and playing around and stuff. But in fact, it is possible to analyze the behavior of these LSTMs also after they're trained, and there was a very recent paper out of Hochreiter's lab where they're actually training LSTMs for some component of playing Atari games, and then they use some analysis to actually try to figure out the most important features of the input and so on. So yeah, this kind of analysis is important. Okay, so that's LSTMs. Now this is the last slide, and then we'll take a break, and then after the break we'll go back to the image stuff. But so this gated recurrent unit. So I think this was introduced around about 2014 or 13 or 14, I'm not sure. So this was, I guess, the thing I should say, it's very similar to the gated recurrent, it's very similar to long short-term memory, but it's only got 2 of these sigmas instead of 3. So people kind of looked at this LSTM. There is something a bit weird about this LSTM. It's sort of, it kind of looks like it's more complicated than it ought to be, because you're deciding how much to forget, and then you're deciding how much to incorporate, and then how much to output. So what happens here is you've only got 2 gates instead of 3, and you're basically, these gates determine the ratio of how much of the previous information you keep versus how much of the new information you add in. Yeah, so it's this sigma here gets, this is basically, this serves the same role as the forgetting part, but then the same activation, basically it's saying, well, if sorry, I'm just, the forgetting, oh yeah, the 1 minus, right. So this is actually a forgetting, component now because of the 1 minus. So if this number is close to 1, then 1 minus it will be close to 0. So that means you're actually forgetting a lot. But then that number comes along here and says how much of the new thing to add in. So basically it's saying, well, if you want to forget a lot of the previous activation, that means logically you would be adding in a lot of the new activation, right? So this kind of is simpler and looks logical, and people have successfully trained this for most of the tasks that LSTMs have been trained for. But as I was saying, we've looked at some just very recent work in the last couple of months that sort of really compares these two and claims that LSTMs somehow still perform better, but it's not exactly understood why. Okay, so I don't have a summary slide, but basically the idea is that as you move from one architecture to the next, you can learn longer and longer dependencies. So the sliding window is very, very short-term stuff. The simple recurrent networks can learn medium-range dependencies, but not long-range dependencies, and the LSTMs and GRUs can learn long-range dependencies. Good. Okay, any questions? So let's take a 10-minute break, then we'll continue our discussion. Okay, so what I'd like to do now is go back to what we were discussing last week about image processing. So there's a bit of sort of I'm sorry that we're sort of crossing a bit back and forth between image and temporal processing, but I do think it's better if we sort of learn the basic architectures first and then have a bit of a week for it to sink in before we really look at sort of industrial size applications. Yeah. So what we discussed last week, we talked about convolutional networks, and we looked at some of the details of AlexNet, which was this network from 2012. And so what I'm going to talk about now is really just, later networks that were performed well for this ImageNet competition, which were deeper than AlexNet, and what techniques were used to allow them to be deeper. So I'm going to talk about weight initialization and batch normalization, and then a couple of different ways of modifying the network architecture, so residual networks and dense networks. And then finally, just a particular application of image processing, which is neural style transfer. Okay, so just to recall, this ImageNet database is, you have 1.2 million images in 1,000 different categories like this. They're 20 color images, 227 by 227. Now, we talked about this AlexNet, so we had some convolutional layers, some pooling layers, and some fully connected layers. And in the details of this, they actually sort of split it up on two different GPUs, and they tried to do it in a way that the two GPUs didn't have to interact too much, so they only interacted at certain layers, which are indicated by these dotted lines. Now, and we looked at some of the innovations that were introduced for this. So the rectified, this was the first time that rectified linear units were used in a serious way. They had the overlapping pooling. They used data augmentation, so they shifted the images a little bit by 1 pixel and that sort of thing to create new images. And we talked about dropout, right? So dropout is a general purpose thing that could be used in any deep network, but they happen to use it in this instance as well, okay? And these were some of the filters that emerged. Okay, so now what happened afterwards? So that was 2012. So in the years that followed, people managed to train even deeper networks for this image classification task. So how do they manage to train these deeper networks? Well, first of all, by weight initialization and batch normalization. So we have to remind ourselves, before we get to the batch normalization, we have to remind ourselves a little bit about statistics. So let's suppose we're tossing a coin repeatedly. If I toss a coin 100 times, how many times do you think it's likely to come up heads? Yeah, so if I toss a coin once, so if I toss it 100 times, on average, how many heads would you expect if it's a fair coin? 50, that's pretty obvious, but the more interesting question is, if you get many people to each toss a coin 100 times and tell you how many heads there were, and then you make a distribution, you expect to get one of these, normal distributions, basically a bell-shaped curve, and then the question is, how wide should that be? Should it be, very narrow or very wide? If you tossed it, I think in the opening scene of that, there's a play called Rosencrantz and Guildenstern Are Dead, where in the beginning the guy's tossing a coin, 50 times, and it's coming up heads every time. Well, you would know something suspicious was going on if you saw that happening, right? So how do we answer this question? So for many of you, this is just a sort of review, but it's important that we all understand this. So if you toss a coin once, the number of heads is either 0 or 1. Right, so the mean is 0.5. Now each outcome, the mean is 0.5, but the actual outcome is either 0 or 1. So the difference between the actual outcome and the mean is 0.5. That's called the standard deviation. And if we square that, we get 0.25, which is called the variance. Now, if you toss a coin 100 times, the mean gets multiplied by 100, so that's 50. But the important thing is that it's the variance that gets multiplied. It's not the standard deviation that gets multiplied by 100, it's the variance. So the variance for one coin toss was 0.25. The variance for 100 coin tosses will be 25. And then if we want the standard deviation, we take the square root of that. So if you draw this bell-shaped curve, the mean is at 50, and the standard deviation is 5, so that means the standard deviation is kind of that point where it measures this, sort of plots the bump in the middle of that bell-shaped curve. So most of the outcomes will be concentrated in this area between 25 minus 5 and between 50 minus 5 and 50 plus 5. So you expect most of the time to get an answer. The number of coin tosses should be between 45 and 55. That's one standard deviation away from the mean. If we go 2 standard deviations away from the mean, like between 50 and 60, the way the bell-shaped curve works is that 95% of the time you should get an answer that's within 2 standard deviations of the mean. So there's a 95% chance that the outcome will be between 40 and 60. So if it's less than 40 or bigger than 60, you start to suspect the coin might be biased, right? Now, if we toss the coin 10,000 times, the mean is going to be 5,000, but the variance is 2,500, so the standard deviation is 50. So it's 5,000, plus or minus 50. So in a way, this distribution, in one way it's spreading out, but in another way it's getting very narrow. So if we think about it in terms of actual numbers, we're going from 5 to 50. But if we think about it in relative terms, the 5 from 50 is like a variation of 10%, but the 50 out of 5,000 is a variation of only 1%, right? So the fraction of, if you instead of counting the number of heads, if you counted the fraction of times that the thing was coming up heads, it's very tightly peaked around 50%. It's 50% plus or minus 0.1%. Yeah. So that the ratio is actually getting very, very narrow. Okay. So what's this got to do with neural networks? Well, okay, so in general, if we measure n random variables, x1 up to xn, then the mean is going to be the mean is going to be if we average them out, then if we add up n variables, the means get added up and the variances get added up, right? So in the case of a neural network, let's think about a neural network, and you've got a certain node, and then there are inputs coming into it from other nodes, and these nodes have activations xk, from k going from 1 to n, and the weights are wk, right? So to calculate the activation of that node, there may or may not be a bias, but if let's assume there's no bias, and there's n. There's n nodes in the previous layer that are connected to that node, then the way we calculate the activation of that node is we take the sum of the activation xk of the other neuron multiplied by the weight wk, right? Now, if we think of these as random variables, then the variance of that number y is actually n times the variance of w times the variance of x. Okay, so let's introduce a few more indices here. So there's a deep neural network with several layers, so let's consider that we're looking at layer I. And we've got weights in that connect that layer to the previous layer, to the next layer, so wi, jk. So you've got ni nodes in layer I, so we number them as xk, I. And then if we want to calculate a node in the next layer, we take a sum here and then apply the transfer function, right? So it's the sum of wjk times xk, and this superscript is just to remind us which layer we're in. And so the question becomes, well, if we assume that all of these things have a normal distribution with a certain mean and standard deviation, then we want to ask ourselves, well, what's the mean and standard deviation of the activations of the next layer compared to those of the previous layer? And the answer is that the variance of this sum is going to be the number of input nodes, the number of nodes that connect to that node times the variance of the weights times the variance of the activations. And then we have to take account of the transfer function. So we just try to multiply by some constant that takes account of the transfer function. Now let's think, it's helpful in this instance to think of let's think about the transfer function as being ReLU. So remember that the ReLU is 0 for numbers less than 0 and then becomes equal to identity for numbers bigger than 0. So for ReLU, we can treat this as 1/2. Like we've got a distribution and we're sort of chopping off the left half of it. So the standard deviation of what remains is roughly 1/2 of the. If we started with a normal distribution that's centered at 0, and then we just get rid of the left-hand side, the standard deviation of what remains is roughly 1/2 of what we had before. Maybe not exactly, but it's a pretty reasonable approximation. Okay. So if we want to have kind of if we want a deep network and we want to have healthy backpropagation through all of these layers, what we really want is that the activations and the differentials should be approximately the same at each layer. So we don't want a situation where the differentials are very big at one layer and very small at another layer, we want to have a balance where the differentials are approximately the same size at every layer, so that the changes in the weights at each layer are roughly the same size, right? So when you go forward through the network, you can apply this repeatedly. So this tells you that when you move from layer I to layer I plus 1, the activations roughly get multiplied by this number here, G0 times Ni times, this is the variance of the weights from layer I to I plus 1. This is the number of nodes that each node in layer I plus 1 is connected to in layer I. If it's fully connected, maybe all of them. And you get this G0. So this gets you from layer I to I plus 1, and then you multiply by this, and then when you go to I plus 2, you'd multiply by this at the next layer, and so on. So you actually, the variance of the output is actually like you take the variance of the inputs and then you multiply by this value for every intervening layer. And when you backpropagate, you do it in reverse. So you take the differentials at the output layer and you look at their variances, and then you multiply, every time you backpropagate, you multiply by the same value essentially, but this G1 here reflects really the derivatives of the transfer function rather than the actual transfer function. But in many cases, the G0 and G1, so in the case of ReLUs, G0 and G1 can both be defined as a half. So again, because the ReLU, if you look at the derivative of the ReLU, it's 0 for negative numbers and it's equal to 1 for positive numbers. So on average, sometimes it'll be 0, sometimes it'll be 1, so it averages out to 1/2, right? So what you want, in order to maintain healthy backpropagation, you want this number to be approximately 1 at every layer. That's what we want, yeah. So at each layer we want the N in, Ni in and Ni in and Ni out. This is the fan in and the fan out. So Ni in is how many layers are coming into this node, and Ni out is how many nodes this node is connecting to. So again, often they're equal. If it's fully connected, then Ni would just be equal. Ni in would just be equal to the number of nodes in layer I, and Ni out would be equal to the number of nodes in layer I plus 1. Okay, so we want this to be equal to 1, and so we can choose the variance of these, at least initially, we can choose the variance of, so this leads us to the idea of weight initialization. We want to choose the weights in layer I from a normal distribution with mean 0, and the variance should be equal to 1 over G1 times Ni out. Yeah. And that should be true for each layer. So we choose that at the beginning, and then hopefully that'll be maintained during the backpropagation. Okay, so this is, and this choice of G1 is important. So these are some graphs that show you what can happen if you, I think this is trained on the MNIST, it's trained on this image recognition task, this ImageNet, and what you see on the left is, excuse me, on the left you have a 22-layer network, and on the right you have a 30-layer network. So, and the red graph represents where you've done this weight initialization with G1 equals 1/2. The blue shows where you've done weight initialization with G1 equals 1. So that's like a wrong number. So if G1 is equal to 1, you could have a situation where the differentials expand at each level. So they could expand exponentially, potentially. So they could double as you go from layer 22 to 21, and then double again at layer 20, or I don't know if it's as bad as that, but they could get bigger and bigger as you backpropagate them. So in this case, with 22 layers, both of them learn, but the one with G1 equals 1/2 learns considerably faster than the other one. When you move to 30 layers, the one with G1 equals 1/2 successfully learns, and the other one fails to learn. Yeah. So this weight initialization allows us to train deeper networks. Any questions about this? Yeah. Okay, now batch normalization is another technique that is based on the same principles. So what this tries to do is it doesn't just initialize the weights according to these principles, but it tries to maintain this scaling during the training, right? So it says, okay, let's consider a particular activation at layer I. Let's consider node K at layer I. And let's look at the distribution of the activations of that node over a particular set of inputs. So if you're doing image classification, let's say we consider 1,000 different images, and we measure the activation for that node for each image, and we calculate the mean and standard deviation of that activation over all of those images. And so then we can kind of normalize this. We can compute this number xk hat, which is like xk hat will have a mean of 0 and a variance of 1, because I've subtracted off the actual mean and divided by the actual standard deviation. And then I can say, all right, well, I want this activation to actually have a different mean and a different standard deviation. I want the real mean to be beta, and I want the standard deviation to be gamma. And so I'm going to rescale, for this particular node, I'm going to rescale its activation linearly so that the mean is beta and the standard deviation is gamma. And so beta and gamma actually become additional variables that we can train by backpropagation. Yeah, it sounds a bit sort of wild, but this actually does work in practice. So the network chooses its own mean and standard deviation for the activations of each node, and it imposes those by calculating the mean and variance over a batch and rescaling them accordingly. Okay, so these techniques get us pretty far. They get us to 20 or 30 or so layers. But then you can make the networks even deeper. So with these techniques, you can probably go up to 100 layers. But then you ask yourself, okay, are you actually getting any benefit out of those additional layers? And at some point, you're not really getting benefit. So you can measure this. You can do this by measuring if you've got a training set and a test set, you can measure the training error and the testing error. And you find if you add additional layers, the training error goes down, but the test error might not. So there might still be a gap between the training and the test error. And this is interesting. This sort of sudden drop here, that is actually something that's often observed with this image classification. Often the training proceeds to a certain point, and then there's like somehow a sudden improvement, and then sort of slow progress after that. I'm not exactly sure why that is, but this is I think it's just characteristic of that task. So people looked at this and said, okay, well, we want to add extra layers, but we want to get benefit out of them. And so there were two innovations that were introduced in the context of this ImageNet competition in 2014 and 2016. So the first, and these ideas have appeared actually in other contexts as well since. So the first one was this idea of residual networks. So the way this works is instead of just having lots and lots of layers one after the other and always feeding the previous layer into the next layer, they introduce these kind of skip connections, and this value actually gets added in here. So, I didn't have an image of this, but you've got to imagine there's like 30 layers here that's divided into 15 pairs of layers, 15 sets of 2 layers. And at each pair of layers, you copy the activation here down to here, and then you're actually adding something on here. So, and you train the thing by backpropagation. Now, what's going on here is that so what are these layers actually learning? Well, they're learning what should be, well, one way to think of it is that the first 2 layers try to do the entire task. And then the third layer, the next pair of layers try to correct the mistakes of those first 2 layers. So at every stage in the network, these 2 layers are just trying to, the previous layers were already trying to do the entire task, and then these guys are just trying to learn a little bit extra to add on to correct the mistakes that the previous layers are making. So in situations where these previous layers are getting the answer wrong, these new layers are concentrating on those situations and trying to add something that'll correct that and make those ones right. And this is happening at every layer of the network. So, these layers try to correct those mistakes, and then the next layers try to correct whatever mistakes still remain. And each layer is trying to refine the answer rather than compute the entire answer. I hope that makes sense. Yeah. So the previous layer tries to do the whole job, make X as close as possible to the target output. Because when you do the backpropagation, the differential here gets copied. Because this is an identity, the differential here just gets copied down there. And then when it's backpropagated through here, the differential will be added here, right? So it's possible for the differentials to use these, to just go back deep into the network by using these shortcut connections. So this is a residual component that corrects the areas from the previous layers or provides additional details which previous layers were not powerful enough to compute. So it turns out that if you add in these skip connections, then you can add more layers and both the training and the test error continue to decrease. And you can get up to about 100 layers that way and get benefit out of all of them. Now, if you want to go beyond 100, there's a slight extra twist here, which is you have to, so in this picture, this is added first to the output of this, and then the value is applied. But for very deep networks, they switch the order of this around. So they first calculate the value of this, and then they add in that afterwards. When they've switched, after they switch the order, this is called a identity skip connection. And if you've got an identity skip connection, then you can go up to 300, 500, maybe even 1,000 layers. You might only be getting a very tiny benefit from the last, I mean, when you move from 500 to 600 layers, maybe you're only getting a small benefit. I mean, there's a sort of cost-benefit trade-off to this, but you could get some additional benefit even by adding very deep layers, right? So I think just going back to this list, right, so in 2012, this AlexNet we discussed had 8 layers. In 2014, the winner had 19 layers, but was built on quite similar principles. This network in 2014, I think, included, I'm not sure, I think this one included skip connections. And then in 2015, there was an entry which did even better, which, this one from 2015 was residual networks that we just discussed. And then in 2016, which I think is the last time I think afterwards they closed the competition because they said the accuracy was good enough. But the 2016 winner used something called dense connections. So the way dense connections work is the following. You have little blocks of typically of 4 layers, and inside each of those blocks, every layer is connected to all previous layers, right? So within this block, this layer is connected to 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 both of these layers, and this layer is connected to all of these layers. So within this block, each node is connected to all previous layers within the block. But interestingly, you don't connect so you don't, if you've got 30 layers in your network, you don't connect every node to all 30 previous layers. You just do it within a block. And then between those blocks, you have some convolution layers and pooling layers. So I think that, people just basically figured this out by experimenting and trying different things out, and they decided that this was this provided pretty good results. So you have these little dense blocks, and then you have convolution and pooling layers in between, and somehow this did even better than those residual networks. Okay. Any questions about this? Yeah? No. This one is purely feed forward. Yeah, it's not, all of those connections are forward from lower layers to higher layers. Yeah, there are. I mean, there aren't any. It would be interesting to. I mean, humans. It's interesting. The human visual system does have. The human visual system is mostly feed forward, but does have a few backward connections. So, I mean, it would be interesting, especially for like video processing and stuff, to have a few backward connections. But people haven't really explored that much at this stage. So these networks are they're still purely feed forward. They don't have any recurrence to them. Yeah.
And is each one of those connections weighted, or are they skip connections?
Each of those connections is weighted. Yeah. So they learn weights for all of those. Yeah. Yeah.
In weight initialization, this is done before starting, or when we are just selecting the weights and then we initialize those weights, like take the mean and the one the stuff.
Yeah. So there's two different for the weight initialization. It's just done at the beginning, but for the batch normalization, it's continuously done. Yeah.
Like back propagation, it's ultimately find out the right weights. So I mean, does it matter much if they use that method of variance and mean to find or initialize the weights that will be processing?
After you've trained, after you've trained the network, then you just. Well, then you don't have to do you don't have to calculate anything over. Right. You have to assume that the. I see what you're saying. I think it's normally just assumed that the distribution for the test set will be the same as for the training set. Yeah, I don't think they recalculate them for the test set. Yeah. Sorry, just to get back to your question. In just after this, in the the last year or two, people have been exploring networks which combine dense blocks and skip connections. Yeah, but I don't know if there's a consensus about the best way to do it or the best kind of combination. Yeah.
In TensorFlow, there's something called dense equals something. Is the same thing, or is the number layer?
In TensorFlow, is the dense? I think that it is. I think that does give you a dense block. Has anyone tried to use that? Sorry? It just means it's a fully connected layer, is that right? Okay. Okay, all right. Well, I just wanted to show you a couple of cool things in the time we have left. So one of them is this neural style transfer. So this is, I find this really amazing. This is, the idea here is you take two images and you want to combine the content of one image with the style of another image. So this is actually, this is one that I generated myself. There's a website where you can just upload two images and wait for a couple of hours and they'll send you back the result. So this is a picture of me hiking in Matera in Greece a couple of years ago. And that's a painting by Van Gogh, and somehow this process takes the content of this and the style of this, and you can see it's pretty good, isn't it? Yeah, like it looks like a painting, but somehow has the content of the original image. It's it does a pretty, this is, I've compressed this image anyway, but it doesn't, obviously it doesn't do the faces very well and stuff, but then again, the faces in impressionist paintings sometimes look a bit funny anyway. So how is this achieved? Well, so here's some other examples. So this is one reference image, and then it's the style of different famous paintings have been added to that image. So this is Munch's, that one's Munch's painting The Scream. This is Van Gogh's Starry Night, and I'm not sure what these other ones are, but you can see the variety here. Now, okay, so let me just briefly explain how this works. So again, this goes back to classical image processing, something from the late 90s, which was called texture synthesis. So what happened here, this image on the left is a real image of coffee beans, and the image on the right is a synthetically generated image that tries to match the texture of the left-hand image. So the way this was done was that, so in those days they didn't use multi-layer networks, they just had features, effectively the equivalent of, say, one-layer convolutional networks. They had what are called convolutional features that were often handcrafted rather than trained. So these features, people might make up a 7x7 array for a feature that computes some kind of Gabor filter or something like this. And so then what they did was they compute what's called the Gram matrix of each feature. So what you do, so remember that the feature, so let's say you have 16 features for the sake of the argument. So these are convolutional features, so you can calculate each feature at every point in the image. And so at every point in this image, you've got 16 different features. And then what you can do is you can calculate the correlation between different features. The correlation is that you calculate for each spatial location K, you multiply, if you want to calculate the correlation between feature 3 and feature 7, for each point in the image, you multiply feature 3 for that point and feature 3 at that point and feature 7 at that point, and you add them all up over the whole image or average them, and you get this matrix, right? So if there's 16 features, you get a matrix that's 16, a symmetric matrix that's 16 by 16. And somehow, I don't know how they figured this out, but somehow that matrix captures the texture of the image. Yeah, at that point. If you have two images for which that correlation, if you have one image and you calculate the correlation matrix and then you generate another image that has the same correlation matrix for those features, then the two images are going to look like they have the same kind of texture. And it's a little bit, it's not actually, that looks very realistic, doesn't it? If you zoom in, you could probably notice funny little artifacts here. Again, I've pixelated it a bit, but if you look closely, you might see things that look actually like a deformed coffee bean, like it's two coffee beans joined together or something like this. The details aren't quite right, but if you just look at it at this scale, it really does look very similar, right? So this neural style transfer does the same, applies the same principle, but instead of doing it at that first layer, they do it at a deeper layer in the network. You know, so remember we've got a deep network. Yeah, so so the first thing they do is they pre-train a convolutional neural network on ImageNet. So here they've used this VGG19 layer network from 2014. And then, so that's pre-trained on all of those million images. So hopefully, so the idea of the pre-training is that these hidden layers should produce features that are very general purpose, you know, that these features are useful for this wide variety of different types of images. And so after that, they take an image, right? So they take the content image. No, sorry, they take the style image, which is this image here, and they feed it into that pre-trained network, and they compute the feature maps, which is really the hidden unit activations at each. So if it's at layer L, then yeah. So there's a lot of different indices going on, but we have to remember which is which. So L is the layer of the neural network. K is the spatial location. So the pixel where the part of the image where that node is located, and I is the number of the filter. So if there are 32 filters at that layer, then I will go from 1 to 32. And they treat those hidden unit activations as the same as those filters in the texture synthesis. So they compute this correlation matrix for those filters, and they call that the Gram matrix. And then what they do, so again, it's exactly the same. It's the same idea as this texture synthesis, but because it's happening at a deep level, it's happening in a much more kind of abstracted way somehow, or flexible way. So then what they want to do is so what do we want? We want an image. We want the image to be close to the content image. So for each pixel, we can take the red, green, and blue component, and we can measure the squared error between those. Right. So we can measure the squared distance between these two images. Right. For each pixel, we can take the red value of that pixel in this image minus that image and square them, and we can add all of those things up for red, green, and blue over the whole image. So we want to reduce that number. We want to create an image such that that number is low, so that these two images will be similar. But we also want, if we calculate this correlation matrix for one image and for the other, and for the style image, we want the distance there to be low as well. So we can calculate the sum of the correlation matrix for the generated image and for the style image, and take the entries of one matrix minus those of the other matrix and square them and add them up. And this here is just a normalizing constant, so this we divide by the number, because of this sum, we divide by the number of filters and the size of the feature maps, just to normalize this. And so we've got our error is a combination of two numbers. So there's the actual distance between the new image and the content image, and then there's this distance between the gram matrix of the new image and the gram matrix of the style image, right? So we add those two terms together, which is shown here, and that's the thing that we want to minimize. We want to find an image that minimizes this sum. And we weight those, we choose a weighting for each of those two components. And how do we minimize this? Well, we actually do it by back propagation, right? So I didn't draw a picture of a neural network, but what you're actually doing here is, given the image, you can, this term is obvious, right? So this is just the image itself. But here, if I'm given an image, I can push it through the network. So the weights of the network are not being trained here. The network has been pre-trained on the image net, and the network weights never change. That's just fixed. What's actually changing is the image itself. Right. So I start with the image, I go through the network to calculate these features, and then I calculate this value here, and then I back propagate that through the network till I get to the image, and then I'm changing the actual image, right? So it is back propagation, but I'm only allowed to change the image, not the network. So it's kind of turning things around a bit. And yeah, it's, but like I say, the results, I mean, I think this was first done, it was about 3 or so years ago that this was first done, and I was just amazed when I first saw this. I didn't think that this kind of thing was possible. It was these Russian, which one, where is this? Gattis et al. This, I think, Russian group. Yeah, so that's the neural style transfer, and there's various, if you have a look, you can see a lot of different kind of, well, it's been applied to video as well as still images, and you can see examples where they've tried to change the weighting, given more weight to the style or given more weight to the content, and you can see how the image changes depending on the weighting and so on. So yeah, this is quite interesting. Good. Okay, I think that's probably enough for today. And next week, we'll look at applications of this recurrent networks and LSTMs to actual language processing. Yeah. Yeah.
Yes, after this, finish my
Do you have a reference or?
You said it would take me 3 hours to do the assignment. It took me the whole book. The reason being, when I was looking to CSC, right? That's not 3 volumes, because that's
not
Yeah, it's just not memory.
so that's that's why they found these random memory errors. And I was like, why?
A lot of it was just like,
I don't use the
I just like stick to the TensorFlow documentation for like 1 second. And it's like that one line.
the TensorFlow.
It took me a little while to figure out you need the matrix for weights. But once I figured that out, like the rest of this
One
is
just
just
one line. Such as
Have you finished it?
a layer.
Ah, yeah.
Yeah, it is okay.
I figured out the problem like why it wasn't working. That's matrix.
I can figure out like like it's just from this film.
I did like at Williams.
I haven't seen this before. Was there a num in the original train dot? Was NumPy imported in the original
Yeah, I saw this.
train.py or not?
Yeah, already just I tried last to re-download the HW and the trim py file. It is also have the same problem.
See these listings, they tell you what each is used for. Oh, cool. So Williams is used for long-running processes and huge functions.
Yeah, that's my friend, and you know, one that's the same problem with.
No, no.
Yeah.
I
don't know.
Have you what happened when you have you tried? Oh, well, it says you tried submitting from the command line. Have you tried logging into a CSE machine and submitting by typing give or?
I'm not too sure.
That's new.
That's so weird.
You sure you submitted?
Could I just?
You sure you submitted the right file and stuff? Or, oh, sorry. It's very weird.
So could I just send my program to?
Yeah, look, if you email it to me, I'll have a look, see if I can try to figure out what's going on.
Or you can just mark this for not from the give the system or something.
God,
Yeah.
don't suggest that.
Okay, I'm sorry.
No module named.
There's no NumPy globals.
Have you tried sending it via Putty and like opening a session?
Yeah, and
like
submitting with give.
Using shell.
Oh, just submit
Yeah.
on the CSE computer?
That's right.
Okay.
Maybe try that because.
Yeah, because I tried this from my friend's computer. It is also the same problem.
Ah, yeah, but you didn't do it from the command line. Or...
Yeah, I'm not doing.
I mean, can you log into the? Can you log into a CSE? Can you upload your? Can you transfer your file to the CSE system and log in? Because maybe it's interesting to try to run it with Python.
Okay, I'll try it on the CSE computer.
Yeah.
And if I also have something, I should email you. And
Yeah.
to find out.
Please email it to me anyway, because I want to have a look. But maybe try doing that and see if we can figure anything else out.
Okay. Okay, thank you.
Sure.
Yeah.
So will this only be marked based on your testing script, or will you have a look and tell us what's good and?
It'll be marked automatically. Yeah, we just don't have the resources to.
Entirely automatically?
Yeah, so what'll happen is it'll.
Because
Well, these tests will. So part of it will be based on just the tests that are done at submit time, but then the training. The CSE machines are so slow that we actually do the training on another machine.
Okay.
So we'll transfer all the files to another machine, which we a 64-bit machine, which and then we'll train it there. Yeah, and then so you'll get, and then you. I mean, yeah, you you need to achieve like
Okay, because
a reasonable accuracy, not a fantastic accuracy,
Yes.
but a reasonable accuracy.
Because I would have liked to have a bit of feedback on how it's better
Yeah,
to
well, if
better.
you want to, if you show me, I can try to have a look.
Okay.
Yeah.
Well, if, I don't know.
Oh, you
I
were
also
saying
had
it's
the-
slow
yes,
too.
Yes,
Yeah,
on,
yeah,
the, on,
yeah.
the, on the GPU.
Mhm. Ah, you can't. Oh, the GPU. So
Yes.
whether the GPU
So
is.
I use
Okay.
the one layer one,
Yeah.
and that's just the warnings from your script, and then it says it's starting to use the GPU, and yes,
Ah, okay. Well, yeah.
that's for the one layer.
You know,
And there it
the
shows that
tutors
it's
might know.
using the
They're using the GPU. The tutors might know more about this than I do, but I'm just sometimes it gives a warning saying that you know that it would be sped up with a different. Okay.
yes.
Yeah, sometimes it gives a warning saying that if you recompile this or that, that it may. Oh, that's the whole thing, is it?
Yes, that's just your yeah.
Ah, it just says
Yeah.
that certain things are deprecated. Ah, okay, so it doesn't say anything about. Ah,
Yes, but I
your
had
CPU supports instructions.
yes, I just looked for this, and it says that you don't have to worry about this if you're using your GPU, because that's just that you can optimize TensorFlow for your GPU, but if you're not using the GPU, the CPU.
Yeah, this is. Oh, okay.
So
Oh,
that's just CPU optimization, but if
yeah.
you're not using the
That's a
CPU,
good question. So you think it is using the GPU?
yes, because it shows
Ah.
to that's it's running. It's
Yeah, I mean for
it's
this
using it.
size, to be honest, for this size of problem, sometimes you don't get much benefit from the
Yes,
GPU.
maybe that's it.
One thing we could try. Have you tried changing the batch size? Or
No.
That
But
might. I'd be interested to see that.
I
So
can-
what is it? 256. Yeah. So.
I don't really know how to change it because that's done in your script, and it's just the total things you have in the
Right.
mnist
Yeah. Yeah.
place. Actually, I didn't try to.
Oh, wait a sec. Oh, okay. Is it?
But maybe
Oh
it's-
no. Oh. Which is that? Is that the conf or no? It's the.
No, it's the one layer.
Oh
So
right.
that's why it's slow.
Oh, so can we run the conf? Sorry,
Yes.
so I didn't mean to close that.
No,
Can you
it's-
try the
yeah.
run the conf one? I'd be interested to see how slow it really is.
Yeah, maybe that's just it.
Ah, okay. There's some. Ah, okay. CUDA could not create CUDA handle. Error
Okay.
retrieving.
So
Ah,
it seems
okay.
it's not
Oh, it's not
really.
really at all.
Yeah, it's not.
Ah, maybe you need to upgrade CUDA or something.
Okay, well, it's just that CUDA is not
Yeah.
working properly.
Oh, okay. She said it ran before, but very slowly. Yeah. See, the problem is, yeah, it could be to do with CUDA. It
works
could be
with
to do with.
on the first layer,
Yeah.
and it doesn't. But I still haven't tried it, so maybe it's just that.
Ah, it is trying to use the GPU. Couldn't create QD. Have you tried Google this?
No, that's the first time I get this error.
Oh, really?
Yes.
That's
a bit
worrying. Have you changed it?
I just yes look for this.
Yeah.
Yes. Yes, I'll just try to reinstall it or install it in better way.
Yeah, I mean, have you got the latest version of CUDA? Or?
Not the latest because on TensorFlow website they say to use.
This is the one that was recommended.
9.0. So I first installed version 9.2 and then saw that I have to use 9.0. So I installed.
Reported driver version. Did any?
I'll just
Did any of you guys get
Did you try to use
TensorFlow running with a GPU on your laptops? Or?
No. Like they say GPU version is not really good, but
I see.
But you don't affect my program.
Wow.
Okay. That's for the CPU.
Did you guys implement the conv layer?
Well, it's like I
still
don't know.
working on
It passed the auto test, but it's just not running on the train.py. I don't know why. I'm trying to fix that now.
I was going to ask if it's slow. Or...
Like in the form, people say it's really slow. Like
Yeah.
some people takes like 2 hours to compile it.
Wow.
It's ridiculous.
Can I have a look at your code? Yeah, I mean, 2 hours sounds like a lot for this. Oh,
So that's just the first part.
I would have expected like 20 minutes or something.
Okay.
Oh, okay. That's where's the convolution part?
The convolution layer.
It's here.
Yeah, I mean, I can't see anything. It looks good to me. I can't see anything that would make it slow. Conv2. Oh, reshape. Oh,
Does the reshaping? It
it's
doesn't really
better
take
to. It's better to have a I think it may still work, but it's better to have a different variable.
Okay.
I think rather than reusing the same variable, I might call this something else.
I can still just feed it.